Welcome to video on CMOS operational amplifiers. So in this video we shall see design and simulation of a two-stage operational amplifier. So this is a specification given for the design of a two-stage opamp. The model parameters given are Kn dash is 110 microampere per volt square, Kp dash is given, the threshold voltages of NMOS and PMOS are given as 0.7 and minus 0.7. The channel length modulation of NMOS and PMOS are given as 0.04 volt inverse and 0.05 volt inverse, and it is assumed that the length of all the transistor is 1 micrometer, and we are asked to find the width of all the transistor, the DC current I5 and I7 to satisfy these following specifications. The slew rate is 100 volt per microsecond, ICMR is 0.8, the minimum ICMR is 0 volt, the unity gain bandwidth is 5 megahertz, the phase margin is supposed to be 60 degrees. So with these as the specifications, we are asked to find the dimensions of all the transistor, their widths, because length is already given. So we have a compensation capacitor of 2 picofarads. So there is a load capacitor of 10 picofarad. Now from the design, of course, these are the values what is being given in the textbook. So even while designing using the equations, most of you got similar values, maybe slight variation in terms of the currents and the W/Ls. Almost they are same. We think that here it may be 22 microampere because you might have taken using the equation this as 2.2 picofarad instead of 2 picofarad. So other than that, these values are more or less close to your design values, and it is almost equal to the values what is there in the textbook. So let us do the simulation of uh, the particular two-stage CMOS amplifier with the dimensions what is given in the textbook, and we should just compare its gain and the. So let me go to the LT points where we have rigged up a similar circuit here. You can see now we have the differential amplifier and the second stage CS amplifier. We have a compensating capacitor which is of 2 picofarad. The output capacitor is 10 picofarad, and we have the tail transistor and we have the mirror transistor. This is the current source, and this is the voltage source which is giving 1 volt and minus 1 volt, the plus VDD and VSS. So let us try to do the DC condition and try to find out whether we are getting a current of 20 milliamperes and 68 milliamperes as per our design, because I7 happens to be, so I6 and I7 happens to be around 62 microampere, I5 should be 20 microampere. So let us compare that using the dot DC, that is this dot OP. So that we have done. So let me run it now. So run, okay, now these are the voltage and current with different transistor. So now we are looking at what is the current at transistor 5. So this is the drain current of 5. So it was supposed to be 20 microampere, but I'm getting only 12 microampere. So this is 12 microampere, which is less than what is expected. So let us also see what is I7. So I7 is also I7 almost close to. So we expected 62 microampere. It's hardly. So where is I7? This is I7. So it's actually 4 point. It's actually 41 instead of 62. So we need to slightly modify the design now. So as it was given in the so what we need to do is we need to do this process now. So you've done the design, now you're simulating, now we need to slightly modify the things. So upon modifying, okay, what all things to modify? Now as you can see from this analysis, so since the drain current of M5 is actually 12 microampere instead of 21 microampere, I need to increase the value of VGS. So in order to increase the value of VGS, so let me change this VSS from -1 to -1.2. So that will actually change the VGS to slightly increased by around 200 millivolt. So let me make it minus 1.2. So let me see what is the current I5. Let me have a look at I5 here. So this is I5. Okay, see now this is 19.5 microampere. We are expecting around 20 microampere. This is fine. So we can continue with this slight modification in the minus VSS as from minus 1 to minus 1.2 volts. Correspondingly, let us see what is M7. That idea of M7 is almost 62 microampere. This was actually 41. Now this is also 62, and that's also almost close to 20 microampere. Now we can continue with this slight modification in terms of VSS from minus 1 to minus 1.2 to make a current of 20 microampere going through M5 and around 62 microampere going through M6 and M7. So let me do the AC sweep of this. So let me change the modulation simulation analysis. I'm just doing the AC analysis. So from 10 Hz to 10 gigahertz. Let me see the frequency and try to find out what is the frequency response and hence find the phase margin. So if I run this, now this is the output. Okay, here let us analyze what is. So let me just take cursor now. So let me coincide this to 0 dB. This is 0 dB here. So corresponding to 0 dB, this is almost minus 59 milli dB, which is almost close to 0 dB. We are supposed to get 60 degrees of phase margin. We are getting almost close to 52.5 degrees. The phase margin is around 52.5 degrees, which is not very bad. We are expecting around 60 degrees. We are getting 52.5 degrees. So by slightly modifying some of the parameters, we can certainly achieve this phase margin of 60 degrees. So we need to do few more iterations as it is mentioned over here. So we need to make a few more iterations so that using this simulation analysis of the simulation, you can modify some of the parameters of the transistor, the overall design, so that we can achieve the required phase margin and as well as the gain. So gain happens to be around. So let us find out what is the gain now. So gain is almost close to 80 dBs. This is the gain. So gain is almost 79.1 dBs. You can actually verify the gain of this particular circuit using GM1 R1 into GM1 GM2 divided by. So we have in the denominator the current of I5 and the lambdas of M. So as you can just go to this. So if you can actually find the expression for the gain, this is the expression for the gain. It is 2 times GM1 into GM6 I5 multiplied by lambda 2 plus lambda 4 into. You can actually find out what is the magnitude of the current, magnitude of that DC gain. So in the dBs it happens to be 79 dBs. So we can actually find out what is its value in ratios by substituting GM1, GM6, I5, I7 and lambda of second, fourth, sixth and seventh transistor. So this way we can able to do the simulation. You can just have a look at the magnitudes or the dimensions of all the devices. So this has a dimension of 1 micron and 20 micron, and this has got a dimension of 10 as the width. This is M3. The M4 is also 10. You can see M1 happens to be 1.79. M4 is 1.79. That's the width. M2 is also 1.79. 1.79. Similarly, M6 is around 62.83, and M7 is also almost similar to that. And we have a current source as per the circuit diagram given in the problem. So that's what we have. So this is 10 micron. This is 10 micro by 1 micro. We have calculated all the values. We are getting a phase margin of almost 53 degrees. The expected was 60 degrees. We can slightly modify the design again and we can get the phase margin of almost close to 60 degrees. So this way we can use the equations that are listed in the previous videos, and for the given specification we can obtain the dimensions of the transistor so that we can able to design a two-stage operational amplifier for the desired specifications.